Hello,
Hello.
everyone, and welcome to PyData Global 2024. We are very excited to have all of you here. All of you great people joining us from around the world today for our keynote. I am Conrad, co-chair of the conference, and it is my absolute pleasure to introduce Peter Wang, co-founder of Anaconda. I believe Peter and Anaconda need no further introductions, and I cannot overstate how much of an impact you have had on every single data scientist out there throughout the years, day in and day out. Peter will be addressing a very topical question that many of us may currently have, which is in our AI future, does Python and data science still matter? So without further ado, let us give a very warm welcome to Peter.
Thank you so much, Conrad, and thank you everyone for joining. Really excited to have this opportunity to talk about this topic. I realize that I've talked about a lot of things about Python, but really on aspects of AI to the Python and data science community, I've not really, you know, um, talked much about that. And so this talk today um, represents, a couple of years of thinking and processing and learning about all this stuff. And so I'm again, really grateful for the opportunity. And thank you for having me. So without further ado, let's go ahead and get started. See, present, share screen, and here. All right. Connor, can you see that?
Yep.
Awesome. So the question today, right? Do Python and do data science matter in this AI future? Obviously we have a lot of things happening in the world around AI. Everyone's talking about it, including people who have no idea what it is. But for us in the data community, people who actually code Python and have maybe been involved in these tools for years, maybe decades, what does this really mean for us? And is data science a thing of the past? Does Python matter? Right? Um, does any language matter for that matter? It's not just a Python thing. It's, you know, LLMs can generate code in any language. They can generate JSON objects. We have AI coding integrated into many of the editors today. So, does any of this really matter? And um, the answer is yes. I've come to the conclusion that Python does still matter, and data science and data analytics still does matter. So they gave me 60 minutes for the slot, um, but really my answer in expanded form is that the reason this matters is because the data community has this, I think, has a pivotal role in steering the development of AI, and that business and investor outcomes may not be necessarily aligned with the kinds of big picture outcomes that we're interested in. That regulators and there's also sort of political opportunists. There's a lot of things happening that are trying to kick this giant fuzzy football of the topic around. But when we move beyond chatbots, beyond AI writing people's college essays, when we really get to the brass tacks of a human future that is driven by AI, um, the data and science community, I call it data and science because it's not just data science, but also scientists, call it quantitative thinkers, business analysts, what have you. Um, we actually have to defend the value of human cognition. So the answer then is yes. And so that's my talk. Thank you. And I think we have 55 minutes for questions. Um, and so maybe yes, maybe 60 minutes, something like that. But maybe one of the questions people ask is why, right? Maybe that's kind of something that would come up. If that's the answer, why? Okay, well, maybe we'll take 55 minutes to talk about why that is, right? But to do that, we actually have to walk through a number of different topics. And I'll start with why Python and why Python for data science. And it was about 12 years ago that Travis and I had this vision that this niche of scientific Python could be transformative for the world. And that intuition was guided by really two things that were happening to disrupt the tech industry. One of them was cloud, and one of them was big data. So the fact that you could rent supercomputers in the cloud, you didn't have to wait for IT to provision, 3 years or 2 years to provision you a rack of computers, and you could also gather much more information, much more data than could be stored, under your desk or in one of these computers that IT would sometimes take very long to spin up for you. So between big data and cloud computing, put them together, and you have a lot of compute. You can throw out a lot of data. but how are we going to do that? Well, we saw more and more people using the scientific Python, the SciPy tools. And so we said, well, you know what, we should probably rebrand this as Python for data. So we created PyData. And then we also created a nonprofit, NumFOCUS, to house and be a fiscal sponsor for a lot of these open source projects. And we created a company, Anaconda, to demonstrate that there was commercial value in this and to provide essentially economics of some sort to sustain this open source community. We cared about that from the very beginning. We tried a variety of different ways to make money, essentially, to put money into this open source community. And I'm very proud to say that over the last decade or so, we've put over $30 million into various kinds of open source projects, whether it's projects that we created and incubated here at Anaconda, or whether it's projects that were created elsewhere that we either hired devs for or that we've just given money to outright. But over the years, it's been really a wonderful thing that we've been able to do with all of this stuff that we created. But one of the reasons why we really believed, why we thought it was so important to have like NumFOCUS and to have an open source community around this stuff is because we could see that numerical computing was an underappreciated area. Numerical computing, most people don't even know that term. And most people in business or investment space who hear that term, up until very recently, it was toxic. It was not something you would invest in. It was sort of a very niche scientists and lab coats kind of area, right? But numerical computing is tremendously different from regular software development. And I've realized that over the years, I have an intuition for this as a physicist and as someone who did a lot of numerical computing and scientific computing. But a lot of software developers actually don't understand, and certainly their managers, they don't understand what the difference is. And so I think it's worth mentioning a little bit again in service of answering that question: why Python? Why Python for numerical computing? And of course, AI is just a form of numerical computing, right? Um, so why does that matter? And the reason that numerical computing is different than normal software development is that normal software development is very concerned with transformation of data types and abstraction of procedures and algorithms. It's not as concerned about the specific values, right? If you think about developing a typical application in a business context, you have some type that you would have from the schema from a database or the data you're reading in off of disk, and then you do some processing on it. You write unit tests around the types. You might test a few kinds of values, but for the most part, your algorithms are pretty straightforward. And correctness is based on functional transformation. It's not really based on the values of the data itself. It's more concerned with the types. But numerical computing, correctness varies tremendously based on the values themselves. And actually, performance can vary wildly depending on inputs. Anyone who's done numerical simulation, every form of machine learning really is a kind of numerical computing. That you may have code that's perfectly good and accurate and works and is great today, but then when things change 2 weeks from now, it's not correct anymore. Now, we don't say the code is broken. We'd say there's model drift, right? Or we'd say, well, we've chosen an inappropriate algorithm to simulate the physics or the engineering in this regime. At this temperature, at this density, with this flow rate, we need to use a different algorithm. So it's not the previous algorithm was we implemented wrong, but just the software is incorrect now because we need a different kind of software. But all that changed was some numbers went into a different regime. So their data types didn't matter; they're still float 64s, but now you have to go to a different kind of software, right? So numerical computing is very, very dependent on the values, and performance is oftentimes an aspect of correctness. That you can get the right answer, but if this code gives you the right answer in 2 seconds, and this code gives you the right answer in 20 milliseconds, this code is actually the correct one, right? And as a result of this, and tied to this, algorithms are frequently pushing the boundaries of performance and hardware capabilities. So it becomes very hardware dependent. And this is something that might offend some of the traditionally classically trained software developers. The algorithms in numerical computing are much more complex. For the most part, if you think about business computing and most of the software that people write, a web server thing here or something else, the algorithms are pretty straightforward. And even the algorithms that are, in your CS textbooks, a binary search thing, red black tree, some other kind of hashing structure. Those kinds of algorithms, they're well characterized, and then they are written, usually consolidated into a library, so no one else has to write it again, and you just link to that library and you use it. But in the case of numerical computing, there's entire books, there's research papers and PhDs PhD theses on how to do a particular algorithm for a particular domain of a problem. These are extremely complicated sort of algorithms. And so if we look at the emergence of the Python data science community and ecosystem, where does that come from, and why? It's rooted in this distinction that classical open source, things that we all use, whether it's old things like Emacs and VI, Vim, and Linux, and newer tooling, the web stack, all of these were written by devs to scratch their own itch, right? That's kind of the term that the free software and the open source community has used for a long time. But with numerical computing, because you needed to both know how to write the code and you had to understand the domain problem that was trying to be modeled, whether it was financial, whether it was engineering or physics or genomics, whatever it might be, the numerical computing folks were off on their own. The CS folks were going out and getting paid hundreds of thousands of dollars to go write web software for various startups and giant multi-billion-dollar companies. And then all these tired, hungry, and beleaguered grad students in the engineering and physics and whatever buildings, the astrophysics departments, they had to go and write their own code and had to cobble together some MATLAB and a bunch of Fortran code. And so the sci-fi community emerged because this beleaguered set of folks had to do it all on their own. And there was the hilarious quote that essentially the sci-fi community advances one burned out postdoc at a time, right? And it was sadly kind of true that many of the tools that we use today were written by people who ended up leaving their careers in their respective scientific fields. But the question then of why did these people choose Python is very interesting, right? Because they could have picked any language, but for them, Python was something fairly accessible. Python was a language they could pick up, and Python has a VM. The C Python virtual machine was very straightforward to extend to connect to classic databases or classic code bases in C, C++, and Fortran. So that power is really what created the base foundation level of the numerical computing and scientific computing world for Python. But the interesting thing is that I've come to realize now, many years later, that Python does have a really unique capability in this, and that it was designed from the very beginning by Guido as a language that people could pick up and learn by example, and you could just read. And some of the things that were Python warts or idiosyncrasies for a long time ultimately became strengths in this regard. And so what I've now seen in the business world, and I even saw this 10 years ago, was that Python was being picked up by people who are not traditional software developers. And we would call them data developers or data analysts. We call data scientists now. But these people in this middle class between the point and click Excel and Tableau crowd and the hardcore software development CS major kind of territory. There was this middle class of people who needed to use computation to get their jobs done. They were not there. They're not getting paid to write code. They were getting paid to deliver answers and to find results and maybe build better models, which have a code component to them. But ultimately, it was about getting a business answer, not building a giant application. And so those people picked up Python. And what was nice was that Python isn't just an obscure, weird language that only those people could use. It's a language that was, maybe it wasn't beloved by the programmers, but the programmer community certainly was familiar with Python. Now I think it's quite liked by the developer community, but it wasn't weird to them like, SAS code would have been. Or if you ask a C++ programmer to operationalize some MATLAB code, they would rip their hair out, right? And on the other side, for the analysts, the Excel business analyst, they can look at Python and they may not be a coder, but they can kind of walk through the language. There, the phrase I use for C is that you're at any given point in time in C, you're one semicolon away from a seg fault. And the Excel user is not one semicolon away from a seg fault in Python, right? So they can sort of look at that and tweak things a little bit and learn from that, which is, the fact that this language is accessible to all of these people is very, very important and was a really great dynamic for them. And so at that time, if we go back to then again the question of why data or why Python, there's big data and there was cloud computing, and we came in and launched the Python movement. And what we realized was that the opportunity we sailed into was what was happening at that time was that IT, with its traditional siloed view of the world, it was blowing up. Every single one of these silos was being disrupted, whether it was cloud computing, whether it was big data, whatever it might be, virtualization, all these kinds of things. And so as these silos blow up, then the actual end users, the practitioners, they end up having to pick up whatever they can grab and try to get their jobs done. And if you look at the evolution of business computing over the last 25 or 30 years, a lot of these new regions that show up in the light blue here, they emerged in the sort of spillover between these traditional three pillars of information technology management, right? So the infrastructure and compute and networking side, the data management, database DBA people, and then the analytics, sort of the ivory tower, statistical computing sort of folks. Between these, there's these internecine regions which then became their own disciplines in a sense, in their own right. And open data science really sat at the intersection of all of these. And numerical computing, the SciPy crowd came out of kind of that region between analytics, high-end analytics, and IT. So if we look at the history of Python and SciPy PyData over the last, I guess, couple of decades, Jake Vanderplas has a really wonderful little slide that just had this little pithy caption for each of these different eras. And that's okay, so that's great. But then, what does that mean for AI? Well, modern AI is all built on these tools, right? At the very bottom layer, you still have Python, you got NumPy. There's a lot of SciPy and core data processing that happens with the traditional Python data science stack and the SciPy stack. But then above that, we have many more layers of domain-specific things in machine learning and in modern AI. So that is why Python, how Python came to be this foundational layer for all of this stuff. But I want to quickly just mention one thing over the last decade as we've watched this open source free technology go into the enterprise and transform how enterprises do their work. There's a few things I realized, and there's this important principle, and this does tie in to the question of AI and why does Python matter in an AI era, right? And this comes down to this interesting, this part of it is around an observation from the software world that's called Conway's law, and it is an unfortunate reality of the world that anytime you have a group of people developing software, the organizational structure of those people affects the kind of software that you build. And this is an old observation. And it was this guy who was looking at how do organizations actually build software. He realized and he noticed that the software architecture mirrored the org chart, right? Really interesting general observation. And what I realized in working in business for so long is that there's another slightly more cynical layer on this, which is that when you look at business data systems and you look at business information systems, they, in the long run, they settle in to mirror the budget structure of the IT groups that have to maintain it. It's not just about the org structure of the software devs who have to talk to each other to architect the system, but the overall information system settles in an equilibrium state that matches the budget structure of the IT group. So the IT group has to manage a lot of different things. Then it's going to try to find commonalities along those different applications and say, you know what, why do I have 15 different databases? Everyone, let's all settle on this particular thing, or let's all, use this particular serving technology or this log monitoring technology. And that is, it makes sense. I don't think there's malice there at all. But what ends up happening is that the optimization function for the maintenance and toward the IT side does not match most of the time. It does not match the goals of the build side. And that's just a observation that I have. It's sort of like a law of gravity of enterprise IT. And that's why these large IT systems that have been around for a while are so impossible to transform and move forward, is because they've been optimized in this other direction. Um, and what's interesting about this is that at scale within businesses, this is a little bit spicy, a little bit cynical, but what I observed is that there are a lot of decision makers who are not worried about being wrong per se. They're not worried about making bad decisions on a technical level, because within really large businesses, there's a lot of room to hide. And the reason I bring this up is because Python has now crossed the chasm into mainstream adoption. And the difference is between the left side of the chasm and the right side of the chasm is that on the left side of the chasm, that early market, what they call the early market of innovators and early adopters, they are folks who use and build on the basis of their own direct experience with the technology. They can evaluate for themselves whether something is good or not good. They can go and read the critiques and balance these things. one of my favorite quotes from Zen and the Art of Motorcycle Maintenance. Right in the beginning, it says, what is good and what is not good? Need we ask anyone else these things? Well, for the people on the early market side, no, they're just going to figure it out for themselves. But once you cross the chasm, the sense making modality of the people in the middle is very much on peer signaling, on what's safe, sort of a CYA, you don't get fired for buying IBM, so on and so forth kinds of things. All of that is the dominant modality of decisioning and sense making in the middle part of the, on the other side of the chasm. And Python has now crossed the chasm. So you have people, many businesses, why do they use Python? Well, because everyone else is. Not because we love it, not because we even like it, but we have to. All the new graduates coming out of school, they're using Python, so we have to. Well, should we use this particular library or that thing? Well, we don't know, but let's go and see what has the most GitHub stars. Let's go see what some TechCrunch article or some other thing said about something or the other. Right? It becomes very much a hype-driven or a second-order discourse-driven kind of a phenomenon. Which for people who are in the open source community, people who are made themselves be maintainers of things, this can be a bit frustrating, right? Because now, you have to go do marketing. When you have to go and not just make the thing, but you have to go and intentionally shift and spin the narratives about a thing. That's for people who are in that early market and the innovator and the early adopter community, something feels very inauthentic about that. It doesn't seem to jibe with our community values. And this is important. Again, this ties back to the AI stuff, I promise. But this is a real thing to point out because I see posts like this sometimes on Reddit, right? Um, and this is I don't I pull things out like this and I call it out not to shame the poster by any means because I can understand why someone would ask a question like this, right? Is there really a chance to land a job using open source contributions? um, and I think maybe many people here on the call may have had these thoughts themselves, like, oh, which projects might be best to show on my resume? So I'm a contributor to this, I'm doing that. And there's nothing particularly wrong about that at all. But it's a different kind of value and ethos than from the people who are in that left side of the chasm, who are doing these things out of a genuine interest and passion and a community conviviality, right? There's very different motivations, and that leads me to the next bit of answering the original motivating question for this talk, right? We really need to go and look into and understand what is the essential thing. Is there a sine qua non? What is there about open source, about software, about communities that we can try to understand? Can we glean something from that? And I'm motivated by again highlighting this particular dynamic and this kind of energy and contrasting it with what I see from my friends and maintainers in the open source community. And so, with that, I'll launch into a tiny bit of a little bit of information for people who you may not think about this very often, but software as a concept, software as intellectual property is relatively new. It's barely 40 something years old. I guess it'll be 50 years old this year, but the Copyright Act of 1976 was actually where, and it became effective in 1978, but that Copyright Act is the thing that makes software intellectual property. Prior to that, code was just code. It was not really protected per se, and it was just sort of a thing that the people who sold you the computer would throw on there to make it usable, right? It's like having recipe cards that go in when you buy a food processor or a microwave or something. But once it became intellectual property, now it's a thing that could accrue value. It's a thing that could be carved out and be held out from other people. Um, and it's just part of the background now, where it's expected. If you go get a job somewhere, you sign the employment contract, or even if you're a contractor, right? There's an assignment of invention and this intellectual property stuff that happens in the contract, and it all starts here with software. And the interesting thing is that property property is a concept. I don't know how many people here on the call have ever gone and read the Wikipedia entry or read the philosophy of the concept of property, but it's not a given that software should be property. And in fact, my argument is that the open source community and the free software movement demonstrates that software is a kind of a thing that I would call unproperty. So what is unproperty? Well, it's not really, there's nothing physical in the world that would give us the sense, because in the world, everything you encounter in the physical world, every physical object, it is a scarce thing. If you have an apple, then I don't have the apple. If you take a bite out of the apple and give it to me, well, that apple is now lessened by one bite, right? If you have a piece of property, it's your property. Sorry, real estate, right? No one else can go build a house on that real estate. If you build a really tall house, you block someone else's view. Everything we deal with in the real world has this scarce aspect to it. But software ultimately is information. It's ultimately a configuration of ideas. It's a rendering or precipitation of pure thought and rendering it, expressing it in some kind of form. And when we share it with someone, it doesn't get lessened. And in fact, if we share it with someone, they can make improvements on it. And now we are further enriched. So it's not just non rivalrous, it's actually anti rivalrous, that the sharing of it increases value. Really a really interesting thing, right? And again, I think it's something fairly philosophical, but it's an accessible concept, right? Um, and so when we think about open source and what is essential to open source software and open source software communities, they are communities of practice. They are human ecologies that swarm around this particular dynamic, just like whatever the worms in the under the ocean around those volcanic vents. When we get together and we make code together, sharing it increases the value. The more users we have, the more chances we get a good bug report, right? Or the chances we find someone that's able to contribute more and add more features. But likewise, forking is actually the thing that damages it. If I like your project, but I don't want to work with you, I take your project, rename it, put some other stuff on it, and now users have to make a choice. Well, do I use Peter's version or do I use the original author's version? And what do I do, right? Forking decreases the value because it splits the human ecology, the substrate of human capital that could be applied to this particular project. So we should, in general, approach software with an abundance mentality. And these open source communities are unique human ecologies that are able to give rise to this stuff, right? It's not about taking, it's about participating. And it's when we look at these open source communities, the ones on the left side of the chasm, what ends up happening is that participation is what gives you voice. It's what preserves your agency, right? If we accept people into this participation culture, we have to develop a human level of trust with them. It's really hard to trust corporate brands. It's really hard to say, oh, well, that brand X showed up and I don't know who it is, but they showed up and they committed this code. You can do that somewhat, but really there's a human element to this that is undeniable, right? And so I think both VCs, venture capitalists, and open source nerds make the same mistake about looking at software. There's an obsession with code because well, from the VC's perspective, they see code as being the intellectual property that you could build a moat around and start making a lot of money. But from the open source developer's perspective, the code is a thing that you spent nights and weekends banging out and making perfect, and it works. So of course, there's a reason why you would cherish that. But actually, the important thing about software is the human ecologies around a piece of software, right? You can have the most genius code in the world, but if no one understands it, no one's around to fix it, no one's answering questions about it, are you going to use that project? Maybe not. You might try to take some of the best ideas from it and put into something else, but you wouldn't. I mean, you could maybe go and adopt it, but even then, right? There's a sense of liveness that is tied to this human ecology, and that's the thing here. That software is actually a relationship. It's your code, your expression, your utterances into a text editor that go and solve someone else's problem. And so a software community or an open source community is the semi-stable pattern that emerges on top of this underlying complexity. And so without getting again too much into the philosophical weeds, these are called Schelling points. In all these other kinds of non-scarce or anti-rivalrous human coordination kinds of terms get brought into this. But it's actually pretty simple when you think about it, which is, are you in relationship, right? There is this concept of right relationship between the maintainers, contributors, and users of a piece of code. Um, and the candle picture on the left, right, is calling out to Thomas Jefferson's famous quote that um, when I light someone else's candle, it doesn't. I'm going to butcher this quote, but basically, when I light someone else's candle, it doesn't diminish my flame any. Now, he didn't really, I guess, speak to the problem we have in the modern day, where we have an abundance of light, right? An abundance of flame and candles, maybe even in the Python ecosystem. But that's a topic for a different day. But anyway, I couldn't have a picture of a candle and be the anaconda guy and not have a picture of flaming dumpster fire around Python packaging. So here it is. There's the joke. But anyway, at the end of the day, there's this, to bring this all the way back from Conway's law about software dev ecosystems to this point about open source software and communities. um, I you know I sort of turn this around on its head and say, well, what why wouldn't we just say that code is then a cultural artifact, and that if you want to change the code, you really have to shift the culture of the people that produce the code, and that maybe it's categorically not possible to produce a code, a software, a human ecology that produces software unless you focus on the human ecology. It's sort of like if you want to grow good wine, if you want to have good wine, you have to get good grapes, and those grapes come from the soil. You really just can't shortcut your way around that. And so in this way, the code is the grapes, um, and the soil is the human ecology, right? And this matters. Okay, this really matters, and this comes just smacking us in the face around this AI thing, which is we see now all the time in the discourse, because AI requires so many GPUs and data centers, and who's building nuclear power plants to go and power these GPUs that go and make these AIs that will rule the world. And you end up with a very, I would say, the ultimate scarcity, which is denying even the agency and importance of other people. And so we have this man of the arena, the great man theory. Is it Sam Altman? Is it Mark Zuckerberg? Or is it Elon Musk that's going to deliver us AI salvation? Right? And that's all fine, maybe in a Twitter discourse or whatever. But people really think this way. And for me, what's discouraging about this is that none of those people built this, right? They funded some people to build this, but the actual human ecology of people who spend their nights and weekends scratching their heads about why some like runtime error or why some precision error in some unit tests on something in the middle of SciPy, what do we do about that, right? That is a human ecology. There's not a microbiology or microbiome in the soil. This is literally the human ecology of the apex predator on the planet, which is Homo sapiens. We get together and create this human ecology, this participatory human ecology that has democratized innovation and that allowed many, many different kinds of interesting and wonderful things to happen. And that's why I think it's really important to understand that there's an alternative to this great man of the arena, a few people, and that's it. And the rest of us, they're gladiators, the rest of us are spectators. And it's like, no, we built the arena, we made their weapons, we did all these things. And this idea of democratized innovation is lost in that particular articulation. The worst thing in an argument is when you allow your opponent to frame you into a losing position. And so I reject that frame. I reject the paradigm that somehow AI salvation will be delivered to us by a few Promethei, I guess. Which is it? Which of the billionaire, trillionaire Promethei will it be? I don't think it's that at all. The fire is not coming down from the mountain. We are the mountain, right? It is humanity that actually has agency in this. But we don't have good ways of talking about that. Even those of us who made the tools that power this stuff, we oftentimes don't have the right tools to talk about it. And so, calling back to some of I gave a PyData, PyCon DE, PyData Berlin talk in 2019, and I made this point that if you look at the human ecology of open source and the anti-rivalrous nature of the unproperty that is software, we have actually, as a community, outcompeted capitalism as an organizing principle. And I'm not like a stark like socialist and all this other kind of stuff. I mean, I think we could do much better for everyone for collective thriving. But in general, I think there are aspects of capitalism and market economies that are great. But if you just actually look at the top line metrics, a group of you know assistant professors and grad students cobbling code together over a mailing list and GitHub. You could fit them all in like a large van at some point, and they create a software that powers billions of dollars of daily economic value, right? So this community, this collective action approach of having a participatory anti-rivalrous kind of culture is able to produce tremendously powerful things at very, very low cost. So in this picture, for those who don't recognize, this is at the first PyData workshop. And we have in this picture the creators of Jupyter, Matplotlib, Pandas, NumPy, scikit-learn. Many people don't necessarily recognize. I don't know if you can see my cursor, but unassuming, modest David Kornapu here is actually the gentleman who made the very first commit to scikit-learn way back in the day. So there's all of these interesting folks, and they grew a community, right? They grew a community of other maintainers. They handed off ownership of their projects, the steering of it. They handed it off to other people, to other maintainers and committers that they trusted. And so this rhizomatic sort of interesting interconnection between all these people created a community of software that went from being again, just a handful of dudes having a workshop meeting in 2012 to now being the most popular language in the world that literally is the language of AI, right? And we did it by being a human community. We didn't do it by any one of these people saying, I'm the man in the arena. No, we just did it by working together. And without, I'm looking at the time here, without getting too far down the weeds, for people who are interested in this, I would encourage you to go and look for the recording, the video recording of my talk. There, it's the PyCon DE PyData Berlin 2019 keynote, and I talked about this distinction between open source for commoditization and open source for innovation. And I'd heard someone make this argument years ago to me that, oh, open source tends to solve well-known problems. And I was feeling very offended by this because I felt like, well, permissionless innovation allows thousands of people to go and try new things and do interesting things. It actually parallelizes innovation, right? It democratizes innovation. But however you want to look at it, in both cases, there is an open marketplace that's facilitated by this. And this, again, I don't want to get too far down the weeds in here, but the point is, my belief at the time, and what I try hard to communicate to enterprise buyers, but also to open source contributors, is the idea that we are building ultimately software. If software is this relationship with an open community, with open source, you give folks a way to dial in what kind of relationship they want. Do they want to rely on someone to provide them secure, guaranteed maintenance updates? Or do they want to go and say, you know what, I'm okay with adopting bleeding edge, cutting edge innovation, knowing I'm going to have to do more work and that things might not be stable. But people get to elect between this on their own. They could actually select what kind of relationship they want to have with the code, with the community, with the maintainers. So, but the thing that I could see even then in 2019, that's just 1 year after the creation of the transformer and the attention is all you need kind of stuff. I could see coming down the pike that the open ML and AI community was going to become more and more dominated by really big, well-capitalized, multi-billion-dollar players. And I asked these provocative questions at the time. Why didn't TensorFlow come out of the sci-fi community? Are Jupyter and Pandas sort of the last great hits of our ecosystem? And what is this? If we're at this point now where, okay, we're this rhizome and everything, but you know what? Mushrooms go pretty close to the ground. And those rhizomatic things, I guess the mushrooms go in trees pretty high up, but technicality, pardon the metaphor breakdown there. But the point is that is this rhizomatic sort of fungal connection, is this really just for the ocean, for the forest floor? And for us to get higher and to go up and to really attain these AI and AGI heights, we have to count on massively funded multi-billion-dollar players to come in and deliver us to salvation, take us to those great heights. Is it possible to have community-sourced, democratized innovation really take us into the future? Or is it really going to be, we pick one of the three denominations of the Church of AGI? It's going to be the Zuckerberg denomination, the Sam Altman, or the Elon, right? Is that all it's going to be, right? So I didn't quite articulate it that way then, but this is really the question that still faces us today. So anyway, I've danced all around this. Now let's actually talk about AI, shall we? So I want to zoom out all the way out and contextualize what's happening today in AI around this two very simple things. Number one, the PC revolution happened. Number two, the internet revolution happened. And both have been about scarcity. right? The PC revolution said, okay, you know what? It's not just 5 computers that IBM is shipping to the world, 5 mainframes. There will be thousands, there may be millions of computers, but computers by themselves are fairly inert. They don't do a whole lot. They're hardware substrate for software. So the scarcity is people who can actually write the software and turn domain context, informal specification, business things all into working code. And working code is really just a very fast abacus, right? On the other hand, we have the internet revolution, which um, the internet revolution, the scarcity there is that, well, as more stuff came online and we connected more people and you could kind of see where it was going to be, getting that data over, getting that information over was hard. Latency is high, bandwidth is scarce, right? These are the two fundamental scarcities. And now we have this interesting thing where, like GPT-4 demonstrated, you can take a picture, upload a picture, and it will write code for you. So that resolves scarcity number one. Now, how well that code works right now, it's okay. It's not great. 70% of the time, it works, but it's only going to get better. And the other scarcity, the bandwidth scarcity, well, you can put the entirety now, apparently, of human knowledge. You can compress and condense it into an LLM that fits on a flash drive that will answer any number of interesting questions. And sometimes it makes them up, but it'll still try to answer the questions. And most of the time, again, most of the time it's pretty close. That's amazing, right? And to then put these two scarcities into perspective, these two scarcities meant that we needed people who were IT nerds. We needed people who were software dev nerds. We had all of this human infrastructure that's needed and human expertise to plumb these things through to manifest the possibilities of a technological civilization. But they were really, capped by these two scarcities. And so, at the dawn of AI, if we think about it, we're unlocking both of those things to some extent. Um, a set of numbers I ran a year ago, I guess, but still probably pretty accurate, which is that if you were to count up all the people in the world who knew anything about IT, computers, code, all of your DBAs, all of your Python, data science friends, anyone who could rack a server and plug it in and boot it up and install Linux on it or whatever, every single person who knows anything about tech, you put all of them together, and it's about 4% of the population, right? So that means if you go into a room of 100 people, 4 of them know anything about the technology that undergirds our entire civilization. Um, so what do the other 96% of people do? Well, they're users. They swipe, they click, they buy, they like and subscribe. That's all they do, right? They can't build. They really can't build. But what AI does is it empowers all of them to actually be builders again. They can actually harness computing on their own terms. And it will change everything. And I'm not, I'm in a room of friends here in the PyData community. I don't need to engage in too much hyperbole, but I really fundamentally believe that we are at this dawn of a very transformative time for our species, really. So I want to give people some numbers around the scope of this transformation, right? 25x, right? So because we had scarcity, I want to just highlight this, because of these two fundamental scarcities, we've had to build in a particular way. We had to build components, modular, reusable bits and pieces. We optimized for maintainability, reproducibility, all these kinds of things. And so it's like the picture on the left, where you create cars from a basket of parts, and you have all these different parts that have to get assembled. They're all just components, however. But at the end of the day, nobody just wants a tire or a door handle or windshield wiper. They want the whole car. And so we have now, we can see just a little bit on the horizon, but we can see where you can 3D print the entire car, where you can actually just go and build and deliver a complete predictive solution. It won't have all the fancy bells and whistles. It may not be as well tested as the modular stuff on the left, but for so many people, if I can just go to my garage, mash the big red 3D print button, and just say, I would like a golf cart, I would like a pickup truck, I would like a bicycle, and I just get the thing, you know what? That's good enough for that's like pretty optimal for like a lot of problems, right? And so if that's where we're at, the question then becomes, well, what will people 3D print, right? What will these systems be that we can have ChatGPT create for us? And I want to sort of draw people's attention back in time now to think about the very beginning of computing, right? Computing really started with prediction. It started with making these like anti-aircraft tracking gun stabilizers for ships and for on the ground, all these kinds of things. It was all about prediction, and in the after World War II is when it really became about tabulation and these business transactional systems. Prediction became somewhat of a niche concern, just counting things, right? Going from pen and paper to software was amazing, right? As Mark Andreessen said, famously said, software ate the world because no matter how buggy the software is, it's still better than pen and paper in most cases. But now that we have gone so far into that realm and now so much of the world is digitized, all of a sudden prediction now becomes the interesting thing again. And as we wire those into sensors and actuators, we can see that this is now going to lead into a cybernetic realm. And the war in Ukraine, as really the first drone war, it's not the last. It's going to be the future of all war. It's going to be drones. Future of law enforcement is going to be drones. Future of farming is going to be drones. The future of pollution monitoring in the ocean. Guess what? Drones, right? So all of these things, these drones are powered by interactive online predicting systems. And the term, we already have a term for that. It's sort of a legacy future term called cybernetics, and it's actually the correct term, cybernetics, coming from actually ironically from the same Greek root as the word Kubernetes, right? Still means about governance, governor, and control. And these earliest computers, the reason I kind of call back to this is because these early computers they were processors, they were not memory, right? There's an analog computer there with a rotating disk and a ball on it that does analog integration and solving a differential equation. The picture next to it is a Soviet era water computer. These were processors. These were just abacuses. And even this one, the Mark One, I think this is whatever Mark One fire control computer for the Iowa class battleships. That was an analog computer. It took all these inputs in, and then it had rotating disks and things like that to actually compute and run the differential equations to calculate how much to track various guns to make sure that they stayed on target as the ship was rolling in the ocean. And so over the last, 50 years, we sort of forgot some of this stuff as we added on keyboards and transistors. We made things like Fortran and C and C++. But really today, we still live in the long shadow of the 70s. We were sort of, for the most part, are sitting on technologies that all are based in, really started in the 70s around, oh, not only can we do processors, but we can also have memory. And we put them together, and now you have something good enough for do business transactional processing. We're still in that PC era, right? But now we're going from prediction to tabulation and back to prediction again, right? From these fire control computers to then Sabre, which is the first really big computer transactional system for doing airline ticketing processing, airline reservation processing, then back to prediction again, transformers, predict the next word, right? So in the 2 years since ChatGPT, what have we learned? Where is AI really going? Well, at the time, I played around with it a little bit, and I was aware of transformers and GPT since GPT-3 and when it was an API and whatnot. But with ChatGPT, I was certainly shocked, as I think many people were, even technologists were surprised at how effective this guess the next word stochastic parrot could be. And I likened it to sort of the Kitty Hawk moment, right? The Wright Flyer. The first time I really got a glimmering of emergent behavior from a very, let's call it, let's be honest, it's kind of a brute force and naive algorithm. But now looking back, I can see that maybe that was an inappropriate metaphor, that it's actually more like a Zeppelin, that we did have heavier than air flight, but we don't, at the time, we didn't really fully understand the physics of flight per se, right? The invention that the Wright brothers had, it was a number of different inventions, but they really tried to understand the flow of air over surfaces. And that's how they got the ailerons, that's how they got the propeller. They got all these things that then made power flight possible. But ChatGPT, I would say, is much more like a Zeppelin that, hey, look, it flies. Oh my God, it's amazing. But didn't fully understand how some of the aerodynamics of that really worked. So since then, I think some of these myths have been busted, right? And when the first year that it came out, everyone was just racing to go and build the biggest possible model, the biggest number of parameters, and all these kinds of things. And we've seen now with quantizations and with things like BitNet and more of these kinds of things that we see that these big models don't necessarily win. And the smaller models, if you actually train them with better data, higher quality data, if you fine tune them with your own stuff, you can get very good performance with smaller and even some of the open source models. And really an important thing, another thing that we've realized as well, is that these data sets and these embeddings are really crucial. Um, the Microsoft Phi model and others are demonstrating, a remarkable level of performance for their parameter sizes. Um, and this is a post, I think, from a Google employee actually, that that points to a really interesting thing that these models, whatever the architecture might be, whatever the hyperparameter selections might be, at the end of the day, um, these models from whether it's Gemini or GPT or Llama, Mistral, what have you, they're more just a reflection of their underlying training data than they are anything about the model itself. And this year, very, very interesting to me, this year, even taking this one step further, I'll skip that for real quick. One step further is that there may be, it seems like there's hints, certainly in some evidence, that we have universal encodings. That is to say that no matter what model you use, the actual parameters themselves, the model weights themselves, are actually to some extent isometric to one another. And that is a very, very interesting thing because, um, well, there's a lot of implications of that, right? That if you have really ultimately all of these models are just reflections of their underlying data, and you can choose somewhat different data sets, but let's be honest, a lot of these models share the same data, and some of that data is problematic. But when you put all those data sets together and you train these like 5 or 6 or 10 or 20 different models, if they're all just sort of like fuzzy sketches and different, slightly different platonic projections of the same underlying platonic ideal, which is the sort of uber representation of all human semantic knowledge and context, right? Well, what would that mean? That would mean that really all these big models are within a certain fuzz factor and a precision factor. They're all really converging to the same weights. The biggest models, the bigger they are, the closer they are to one another. Smaller models that are more specific actually may be more different from each other. But the really big ones, they all start approximating the same thing, almost asymptotically converging to the same underlying platonic model. And if that were the case, I'm not saying this is the case, but there's evidence, there's suggestions that this could be the case. If that is actually the case, then we have a very interesting phenomenon. And this gets back to the software's property. What if it was the case that the very biggest models, they're as essentially all converging or being approximations of the same underlying platonic ideal model? What if it was the case that you couldn't really render them into property at all? You can't turn common facts and knowledge into property, right? The square root of 2 is not something that I can trademark or say, well, it's mine and no one else can use the square root of 2. That's just human knowledge, just like the digits of pi. So think about it for a second. What if it was the case that computing the trillionth digit of pi became an immensely valuable commercial thing? Well, once someone has computed it and they say, well, the trillionth digit of pi is 7, that fact itself is no longer a piece of property that anyone can protect. It becomes part of the common knowledge of humanity. Well, that's a very interesting thing. That means that all these billions and billions of dollars that are being poured into making the biggest LLMs are all basically building a convergent, non-propertizable, non-defendable thing that is really the birthright of all humans, right? So that's a very interesting thing that I'm tracking. But you can see where maybe you start to see how this connects, right, to the idea of software's on property, and where this may be a bit of a rejection of this idea that only these great men in the arena can deliver us to an AGI future for humanity, right? Because we also are starting to understand when we first came out with the Zeppelin, a few years ago, we didn't understand how it flew. You take this kind of thing, you do that other thing, you do this other thing to it, you put it all together, and all of a sudden it can spit out Eminem lyrics. Okay, well that's amazing, but how does it do that? We don't know. It's a giant tensor, and you just do a dot product. Okay, that's kind of like magic. But now we're starting to see, just earlier this year, right? We're starting to see that no, there are approaches we can use to take this giant mess of vectors and start to converge them and build, eigenbases out of them, semantic eigenbases, and have linear representations. And we say, well, this model knows about these concepts, and I can squash that concept, or I can really amplify the other concept. So this really blows apart this fiction that we have this magical distillate that allows this stuff to fly. We need to give these great men a few $1 trillion to go make this and liberate us all. No, we can actually understand how it does this thing. Now, the flip side of this understanding is we may start to question our own humanity and the value of human cognition, but that's a different philosophical problem that we, talk about in a bar or something afterwards, right? But this is kind of the cutting edge of research right now. So people looking into linear representations, looking into what's called monosemanticity. Can we identify a eigenvector that means one thing, right? And if we can, and you just do that a million times, now you have a million concepts spanning the conceptual space of humanity. So if you put all this together, what does this mean? Well, in my view, AI models are going to get much smaller, much more efficient. Not only through quantization, not only through inference time optimization and tuning, but just look at the proof point. All of you on this call today, you're powered by really a mere 20 watts, right? Um, so we have a proof in principle. We have an existence proof, actually, 8 billion of them, that we have human level computation running on 20 watts. So we should be able to do much, much better, at least 3 orders of magnitude, if not more, on what we do with these neural nets. And the fact that we can quantize them, like there's a recent paper where they just dropped half of the attention layers out of Llama, and it only lost 2%, 3% in performance, right? There's BitNet, which goes from, right now people are quantizing to FP8 or the 5 and 4-bit quantizations. BitNet goes to 1.5-bit quantization, and it still kind of works. So we clearly have a lot of room to grow in terms of compressing these models to be much smaller. And that means that many people will be able to train up models on their own data sets, including public data sets, right? And so big, huge foundation models will still be a thing, but the new hardware and algorithms will absolutely outcompete existing transformer technology, right? And so the real upshot of that is that AI innovation can be democratized. It can be democratized. We have composable models. We can use community and crowdsourced data that is transparently licensed. We can do inference time scaling and distribute that out so that we can have like SETI at home style, many people predicting and fine tuning and tweaking, evaluating models. And we have distributed training as well. This distro work from News Research that just came out this week, I think. They've been working on it for some time, but now they've created a 10 billion parameter model doing distributed training. So AI innovation can be democratized, which then, of course, where do we go from here, right? Here's the AI train. Everyone jump on the hype train. It's a democratized train. We can go there. But this train runs on data. At the end of the day, all of this so-called AI runs on data coming in to particular algorithms to generate some kind of an inferential model, right? And all data, I say this to everyone, I can say it too. We have to start looking through the concept of data. We have to start sort of seeing through that concept because there's no such thing as data. There's only frozen models. All data comes from some process that was created by human or by machine, but that process distilled some bit of this infinitely dimensional, infinite textured world, and it turned it into some quantized representation. They're all measurements. And what we do is we spend all our days building better and better rulers, and we can use AI to help us build better rulers. But the AI train, to go back to this image, the things that hold up the rails and the rails themselves, the entire track, all of that is data, and that is all intentionally built with humans in the loop. Humans and human intuition, we created the models. We chose which model out of a million models to create to go and produce particular data. The picture here on the right, most people probably don't recognize what that is. That's a close-up of the CCD sensor on a standard camera. And even then, you see there's a red and a green and a green and a blue over every pixel because CCDs are not they're not color sensitive, right? We put what's called a Bayer matrix of RGB masks over the pixels, and then we read that out in the firmware of the camera. You get colors. This really driving home the point that even a photograph is still a frozen model. So we have, as data people, as data scientists, right? We have a role to play, right? Not only in determining how we're capturing the data, what is interesting to quantize, where to put these trusses and trestles, where to lay the rails in this giant wilderness of the world. But these hypotheses, we're also the ones kind of generating the hypotheses, right, that then lay out these models. So in the world that we're going to is a world of computational decisioning, right? You have computers, these models, whether the LLMs or whether some kind of future model, they're all working with people to make decisions in the loop. And sometimes that OODA loop is very long. It could be making strategic decisions for a business. Sometimes it's very fast. It's running on a chip to decide how to steer a particular craft through the ocean or through the air. But ultimately, if we build these cybernetic systems, The role that humans play is that we actually can synthesize. We actually have to govern and steer this holistic approach. We cannot have this siloed approach anymore. It's not just going to be an AI LM that just goes and does everything for us. We actually have to lay out the same processes that we've done all along for data science or for machine learning. We have to hold the line and demand explainability, accountability, governance, and governability. Um, and if we do that, then we actually have, we can actually steer this thing towards a different reality than I think where the narratives currently are pointing towards. And this is why Python, why the Python community, why the data scientists and the data science community, why the scientists, why we have not just a small role to play. We're actually in the driver's seat on this. We decide what is data. We decide what are appropriate ways to use models. We decide how to evaluate those things. And we don't have to wait for trillion-dollar great men in the arena to tell us what we can do. AI innovation absolutely can be democratized. It's on us to take that democratization potential and reduce it to a set of really good generative and participatory practices. Because if we don't, right, we're not doing this alone. We're not in the world just by ourselves. If we don't, then there absolutely is a lot of energy towards doing it the other way, towards making it into a captured system. And that's not only from greedy business capitalists, it's from political opportunists, it's from various kinds of aggrandizing sociopaths. It's all sorts of people who want to say, I'm the savior of AI. But as a community that actually built all the foundational pieces to make this possible, we also have power. And in fact, not only power, but we really have a responsibility to lean into this power that we have. So with that, again, my answer to the question of do we have a role to play is yes. I want to thank you all for your time. Sorry, I'm a couple minutes over here. And I have to plug two more talks. One is my talk on Python packaging from PyBay, and the other is this tutorial that Chris Laffer will be giving on PyScript tomorrow. So please, I hope you show up for that one. And with that, thank you very much. And I think we're out of time, but I can stick around if people want to ask questions.
Brilliant. Just in the interest of time, I think there are other talks that are happening.
Oh, okay.
So
Great.
let's not steal the attendees from those talks. But
Sure.
thank you again, Peter, for your many insights. I think your sharing has given us a much better idea of what the future will bring with AI. I think it has also raised even more questions for us to think about, which is the hallmark of a great talk. Thank you again, everyone, from all around the world for joining us today. Just some housekeeping notes. A recording of this session will be available shortly afterwards for rewatching, and you can also head over to our PyData Global Discord to continue the discussion. Thank you again, and goodbye.
Thank you.